So the really cool thing about IO types like Zio is that they let us continue to reason about our code using these concepts of referential transparency and algebraic substitution. And I talked about referential transparency before, so I don't want to get into it again too much here, other than to say that when you have a pure function like this, where you're just getting the length of a string, but anytime you pass in a string like foo, which has 3 characters in it, the result is always and forever going to be 3. And in the history or the future of the universe, that's never going to change. And a cool thing that I noted before is that anywhere in your code where you have this or the number 3, they're all exactly equivalent, and they will always and forever have that same value and mean that same thing. But then if you contrast that with an impure method like readline, you're reading input from a user, and that input could be an infinite number of different things. It's almost always going to be different. If you prompt people for their names, you're going to get millions of different answers just with that alone. So this is an impure method, and this is a pure one. And because this is pure, as I noted before, we can use algebraic substitution with it, but we cannot use algebraic substitution with something like readline, which is impure. And in the functional programming world, this is bad because we want to write all of our code as algebra. So the question became, what can we do? And that's where Eugenio Moggi came up with or invented this concept of applying the monad to programming. And again, here I have a bit of an error in that I say that the Haskell people invented the IO type. The Haskell people did apply the IO type to Haskell, but Moggi is the one I do need to give credit to for inventing this concept. And then the Haskell people for initially applying it in Haskell. And then everyone in the Scala community who has applied it to Scala in functional programming libraries like Zio and Cat's Effect. So here I note IO comes to the rescue, and I'll come back to this code in just a little bit. A couple of lines I want to note here are that IO is going to be like a wrapper, and it's going to be like a lazy wrapper at that. And what I mean by that is that the code that you pass into IO won't be executed now. It's going to be executed sometime later. And that's what we mean when we start talking about things as a blueprint, because nothing happens right now. We're just creating this blueprint of what we want to happen. And later, when we actually say, okay, go ahead and run everything, that's when things will be run. But as you're programming, you're just creating this blueprint. And then I note that another way you could think of as IO is you could think of it as a wrapper, but maybe more a bit like a box and a bit of a time machine. And again, that's because right now when you do something, nothing happens. What you're doing is you're creating instructions for something to happen later, but right now, nothing happens. And I note here an IO is like getting a receipt from Amazon. Yes, your package will be delivered. And with an IO sometime later, it will be delivered. And if it's delivered just fine, we know that right now is either's happy case or the right value. But if it's not delivered fine, we know that if it's damaged, that's going to be either's unhappy case or the left value. Unfortunately, if the package gets lost, that doesn't fit in well with my analogy, but in these first 2 cases, we're in good shape. So on this page of the book, I talk about IO being a wrapper and how it feels like a blueprint, and then how you can also think of it as being a time machine. And then here on the next page, I continue to talk about laziness and how laziness helps us keep thinking about our code as algebra or being a blueprint. And so we do all this stuff and we're just being very lazy. And then finally, when we come to a place where we say run, that's when the blueprint is actually run. And Haskell, and I don't want to get into Haskell too much, except to say that it does have this magic incantation that says, okay, I'm ready to run the blueprint now. And you don't have to worry about any of that Haskell part because I'm going to show you how to do all of this with Zio in the upcoming videos. So having said all that, I want to back up just a little bit here and then reorganize things slightly. So let's move that over here. And here we have the Ammonite REPL, which I've already started up. And what I want to just show you is that if you type something like print line in the Ammonite REPL, like that, if you type in print line and then hi, it goes ahead and prints hi right away. But now if we bring in Zio, and this first line is the way of saying inside the Ammonite REPL that I want to use this version of the Zio library. And then here I want to import zio.star so I can begin using it in my code here. Now, instead of using print line, what I can do is create a different print function. And for lack of a better term, I'm going to call this a blueprint. How about that? So blueprint is going to be a function and it can take in any type. And I don't want to concern myself with the return value right now, so I'm just going to say that's going to equal, and this is where we finally get into some ZIO code. So instead of creating something like an IO like that, what you do with ZIO is we will say ZIO.succeed. And the reason for that is that the code that I'm about to put inside the parentheses can't fail. So that's why I use succeed there. If the code inside of there could fail, then you would use attempt instead. But since it can't fail, I'm going to use succeed. And just a little bit of extra spacing there so we can see what's going on. So inside here, I'm just going to call println. And you just saw how println worked right here. And now I'm just going to wrap it inside this ZIO.succeed like that. And it shows that I defined this function called blueprint. So now I will say blueprint, and I will give it a string to print. So I'll just say hello. And, well, that's different, isn't it? Instead of seeing println print hi like it did right there, it didn't print anything. Here it did it. In fact, what happened was the result of this expression was assigned to this new variable res5. That's how Ammonite and other REPLs work, is that if you don't declare a variable over here, it creates a variable for you. So it created this variable named res5. And this variable has this type right here. And we'll get more into ZIO types in a little while. But having seen either before, you're now fairly comfortable with this because either had two types in it. It had the right and left values. And now ZIO has three values inside here. And we'll talk about that shortly. But the most important part is this code right here. And it'd be really fascinating if instead of being called sync, if that was called blueprint. But this code right here is the blueprint for this function right here. This is basically a data structure that describes what will happen whenever blueprint is called. But the important part for right now is to notice the difference in the laziness. When I ran println up here with hi, it printed that right away. But when I passed in hello to this function right here, and it still goes inside the println here, so you're thinking, well, that should have run right away. But because ZIO and other IOs are lazy, nothing happens except for the creation of this blueprint right here, or more accurately, this data structure right here. And this behavior that I'm highlighting over here is exactly what I was writing about in the book over here when I said that IO is like a wrapper. Well, that's exactly what's going on here, is that ZIO, and specifically the ZIO.succeed function, is a wrapper around this function right here. So ZIO in this case is essentially keeping println from running right away. And it says, I am storing this as a blueprint that whenever I'm properly called, I will run this. But right now, this is just a blueprint. So I mentioned that over here about it being a lazy wrapper, and I describe how that's a blueprint and how you can kind of think of this as a time machine because, again, nothing happens here. And the only way this is ever going to be run is when you get to the magic incantation of telling your entire application, okay, now it's time to run. But until then, essentially nothing happens other than the creation of this blueprint. And now what I want to do is go back to this other book. And again, this one is called Category Theory for Programmers, and this is the Scala edition. And I should mention that this PDF is freely available on the internet. And if you come down here, this is page 244. And there's a very interesting discussion that starts right here. So I'll unhighlight this, but I want to let you know that this is the interesting part of this discussion right here. And he notes here that a function like getChar, and again, this is in Haskell, if it returned a character that was typed at the keyboard, that couldn't be pure because that character could be many, many different things. And then he notes, but what if it returned that character inside of a container? And then as long as there was no way of extracting that character from the container, we could claim that the function was pure. And that's because every time you call getChar, it returns exactly the same container. And so he has this discussion on this page, and the next couple of sentences here are probably relatively easy to understand. Then he gets into some things I haven't talked about yet. But if you go over to the next page here, I should note that anytime he mentions the word arrow, that's basically equivalent to a function. And if you use the argument that I'd highlighted on the previous page, he adds the discussion here that it's essentially pure functions, and then it becomes pure functions all the way down throughout our code. And then the dirty work of getting inside of these IOs over here is relegated to the system. And the way things work in Haskell is when you have a main function, that's when it says, oh, okay, now I'm going to go ahead and run all of your code, including all of these IO actions. And he notes that when main is called, it will finally start doing all these, he calls them nasty things like reading user input, modifying files, and printing output, formatting a disk, and so on. Only when main is called will this code that I have highlighted in blue over here, that's the only time that would ever be run. And so what I'll do over here is, if you want to read this page or the previous page, just go ahead and pause the video here or rewind it to see that previous page. One other thing I want to add also here is don't get too lost in this theory. If you're reading this page or the previous page here, and this sounds a little bit too nebulous, where we talk about what if we return the character inside of a container and there's no way of extracting that character. If this discussion just sounds too nebulous, for lack of a better term, don't even worry about any of that stuff. Personally, I got caught up in this stuff for quite some time, and I don't even really like to think about it that way too much anymore. I just like to focus on the fact that I'm creating blueprints, or if you want to think of this as being a data structure, I'm creating these things over here. So anywhere in my code where I call this function and nothing happens, I'm just really comfortable with the fact that when this code is called, it just creates a blueprint. And you create this series of blueprints anytime you're dealing with code that involves side effects. But also I should add that if you are a mathematician and you want to think about this as being a box that you never look inside, there's nothing wrong with that. I just don't want you to get too caught up in that way of thinking, at least until you start writing more code and you see how it works and you feel how applications work.